In the next exercise, we return to a familiar setting. Let n and m be positive integer. We have an n by m grid of lamps. Again, rectangular grid. We no longer require n and m to be at least 3 or something. This is a different exercise. A line shall mean a row or a column of the grid. So there are n plus m lines in total, n rows and m columns. We say that a line is bright if at least, so if the line has at least as many turned on lamps as it has turned off lamps. In other words, if the average lamp in the line is turned on, so to speak, or at least more, if the average brightness of a lamp is 1/2 or larger, so to speak. We start with an arbitrary state. Unlike the previous lamp exercise where we started with all lamps being off, this time we start with something. For example, this state. This is n equals 3 and m equals 4. Now, in a move, we can pick a line and flip all lamps on this line. And as before, flipping a lamp means turning it on if it was off and turning it off if it was on. Question: can we achieve a state in which every line is bright? Can we do this by a sequence of moves? So let's do this by an example. Let's do this on this example first. So we have 7 lines here. This first column is already bright because 2 of its lamps are on and only 1 is off. 2 is bigger than 1, so it's bright. This one, however, is dark as it could get. So let's flip it. Now it's on, and so now it's bright. This one is also dark, so flipping it 1, 1, 0, we make it bright. This one is dark, so we flip it 2, and it becomes bright. And now these 2 lines are bright. For example, 3 and 1. 3 is bigger than 1, so it's bright. Now this one, yes, it's also bright because 2 is 2. This is saying at least. This is not saying precise. This is not saying exactly as many. So this one is bright. So we're done. But let's do this in general. So I suggest a method for doing this. And the method is very simple. Keep flipping bright, so keep flipping lines that are not bright. And this is the whole method. So basically, as long as whenever there is a line that is not bright, you pick such a line. Maybe there are several, you just pick one of them and you flip it. So you flip all lamps on this line. So in other words, as long as there is a line that is not bright, pick such a line and flip it. So flip every lamp on this line. Why does this work? I claim that this procedure will stop at some point eventually. Because if it went on forever, if it were, for example, if we would go around in cycles, this would not be a useful procedure. We would never get to a point, to the desired state. However, I claim that it will terminate, it will stop. Why? Because every move in this procedure increases the so-called total brightness. So what is the total brightness? It is the total number of lamps that are on in the grid. Now, if you look back at this example, so this is a non-bright light. It has fewer on lamps than off lamps. If I flip it, then it becomes the other way around. Now it has fewer off lamps than on lamps. So I have turned more lamps on than I have turned more lamps off. And therefore the total brightness has increased. So, and I can be more precise, it increases the total brightness by at least 1 because it's an integer. So if it increases by at least 1. Now, the total brightness of a state is a non-negative, is an integer between 0 and an m, because an m is how many lamps we have in total. We cannot have more lamps turned on than we have lamps to begin with. So it cannot get increased by at least 1 more than an m times. It would just go above an m if it did. Thus, we cannot make more than an m moves sequentially, of course, so successively. And therefore, the procedure will stop. And fairly quickly, as such algorithms go, after an m moves at most. I suspect actually the real answer is even smaller. I suspect you could probably get by with n plus m instead of an m or something, but I don't know, I haven't checked. Anyway, the procedure will stop, and once it has stopped, we cannot make any more moves, and this means that there are no more lines that are not bright. In other words, all lines are bright. And this is exactly the kind of state we want to achieve. So we are done.